Hi guys, this is our online lecture for Calculus 2. Okay, first of all, we refresh what we studied before, namely natural logarithm function, and we're going on to study the inverse functions of natural logarithm function, that is exponential function. Start from the graph. From yellow color graph, which indicate the graph for the natural logarithm function. So we make a reflection along the line y equal to x to get the green curve, which indicate the y equal to exponential of x. This graph can be treated as the definition of an exponential function, namely exponential functions of x is the inverse functions of the natural logarithm function. Alright. Okay, next. Alright, so this is the summary of what we have just now. Y equal to ex can be written as a expx for simplicity. It's the inverse of the y equal to ln x and vice versa. In other words, the ln is actually a log base e. Okay. There are two important identities we need to know by means of a logarithm exponential are inverse functions of each other. Okay. The first one, the voices in this way. Ln of exponential of x give x, or ln bracket e power x equal to x. Yeah, this is the first identity. And the second identity is we take the ln first and e later. So we have e raised to the power ln x equal to x, or exp bracket ln bracket x equal to x. Yeah, we are going to apply these two identities in today's lecture, namely to solve the demo exercises. There are altogether two main categories. The first category is tutorial 5, page 54, which is consists of question 1a, question 1c, question 3b, and question 4c. Just to familiarize us with the two identity we have already brought out for your attention. Next, the second category, we move on to higher difficulty. So at demo exercise, that is use one of these two identities to evaluate the limit of x raised to the power tangent x. So when x approaches 0 from the right. Okay, let's start our demo. Okay, are you ready, guys? Okay, so first type of the questions, familiarize the two identities using the first category, the demo exercise. So focus on page 54, and we're going to start from question 1a. Alright, the result we based on is e power ln star give star, and therefore e power ln 7.2 gives 7.2. Very straightforward. Okay, so question 1c now. To solve the question 1c, ask ourselves what is the ln x minus ln y. To simplify the two ln, so as one ln, to have ln bracket x over y, and therefore the answer for e power ln x minus ln y equal to x over y. Any problem so far? Or so far so good? Question 3b. Okay, double ln, then e power e. When we solve the question from left to right. It should be from right to left, namely from inside to outside. Solve ln e power e, we have Okay, so ln e power sun equal to sun. Therefore, ln e power e equal to e. No confusion. And e equal to e power 1. And therefore, take the ln again. Ln bracket ln e power e will give. Think about that. Okay, just like ln e power 1 equal to 1. So question 3b is solved. Okay, now question 4c on page 54 as well. So we have ln of exponential to ln x. Straightforward, give the answer to ln x as a circle. Done. Okay, come to the more complicated or the challenging or interesting the demo. Okay, how to solve the limit of x power tangent x for x approaches 0 from the right, which carry 0 power 0 form. Okay, so you can see the illustrations, how to get the 0 power 0. So the green color and the blue color illustration. Okay. And in this case, so the form 0 power 0 or interpreted as a very small number in magnitude. Raised to power of a number is also small in magnitude. What will we get? Most of the time, or all the time, there's no conclusive, and therefore we call this form is an indeterminate form. In order to solve the indeterminate form of this limit problem, so we just use the second identity we have, so the control, that is e power ln star. So the question now is limit x raised to power tangent x for x approaches 0 from the right. So that's just a recall. So to solve this, so we focus on the x power tangent x to put in the form e raised to power ln x power tangent x. Alright. And we would get eventually x power tangent x can be rewritten in the form e power tangent x multiply ln x. Can you follow? Right, then with this form we now bring in the limit, the effect of the limit x approaches 0 plus, and we would have the limit with the circle and the power with the circles of blue. Okay, what does it mean? Alright, so you can see that here. So I'm going to bring the limit on top of the e, or in other words means that exponential is a continuous function. So it depends on the input tangent x ln x. So the limit is equivalent to, look at the next slide. Then, so eventually the original problem will be written into the e power. Then you can see the limit already is also raised on top that. So, or in other words means that we reduce the problem of if we can solve the limit tangent x ln x when x approaches 0 from the right. So we solve the original problem. Okay. This is quite a common practice in mathematics. So to restructure or reform the question, and so from the new form of the question here, then we solve the question easily. Okay. With this, so bear in mind with the tangent x equal to 1 over cotangent x, then the limits of tangent x ln x will eventually can be written as so ln x as a numerator divided by the cotangent x as a denominator. Yeah, which also reminded us also from what we studied in MAT 132. Alright, L'Hopital's rule. So L'Hopital's rule can be applied whenever the So the limiting value is in the numerator over the denominator form, and also carry the indeterminate form of the 0 divided by 0 or infinity divided by infinity. Right, in this case, what will we see is that the ln x will eventually goes to negative infinity, while cotangent x will go to positive infinity. So it supports the hypothesis also to run L'Hopital's rule. So namely, we're going to differentiate the ln x separately, and cotangent x separately. Alright. Okay, thus differentiate the ln x separately, we get 1 over x. Differentiate cotangent x separately, we get the negative cosecant square x. So where cosecant square x can be written as a 1 over sine square x. Alright, so simplify this expression over x over the negative 1 over sine x whole thing squared. We are going to have the form as easy as this. That is ln x over cotangent x eventually, so that can be written as a negative sine x over x multiply sine x over 1 under the limit. And again here, recall the MAD 132. Sine x over x will approaches to 1 as x approaches 0 plus. Alright, and then the sine x will become the sine 0 as x approaches 0 plus. And so don't forget there's a negative outside. So negative times 1 times 0. So we will still get the 0. So therefore the limit for the tangent x ln x, so when x approaches the 0 plus, is actually 0. Okay, remember this is the power or the index of the exponential. Therefore the final answer for the limit x raised to the power tangent x, or x approaches 0 from the right, is equal to e power 0, and e power 0 itself will give 1, and therefore the final answer is 1. Okay. Do you understand? Yeah, the approach also there like this, so we will carry on to other indeterminate form beside the 0 power 0. Okay, so where are they? Yes, two other forms can use the same approach are the indeterminate forms of the, so one raised to the power infinity and the other one is the infinity raised to the power 0, with the typical example given. So the former will be given by the example limit for 1 plus x raised to the power 1 over x when x approaches 0. And the second one or the later, so it can be illustrated by the example limit x approaches to infinity for x raised to the power 1 over x. Alright, so now guys, you can also start to do your online MCQs. Alright, okay, and in short, so that's just a reminder for you. So just now the approach we are using here, it generally can be summarized as this. The limit for y when x approaches to a, in this case a can be the infinity or minus infinity, so is eventually equal to e to the power limit x approaches a for ln y. Okay, using this approach, good luck. Tata, and end of the lecture 4.